Everyone, good morning. I'm going to allow just a minute or two for all the attendees to trickle in. And we're actually going to get started right away today, getting right into the materials, getting right into some labs, continuing from where we left off yesterday. So I'll just give one more minute and then I'll start sharing my screen and we'll start going through the next round of content. All right, that's good enough. We'll kick it off. All right. So the next section we're going to cover is going to go more into the operational side of working within the data lake, some kind of administrative aspects of this, like how to best approach implementing the data lake and how to actually structure the data there, and then how to use tools like AWS Glue to crawl data sets and run ETL operations. So Glue has kind of started off as a very simple, straightforward service and has really grown into quite a complex tool for ETL workloads. It can really do a lot these days in comparison from where it came from. So we're going to go over a few of the different components for Glue and just kind of reviewing this kind of a data lake structure on AWS and how we as administrators would go about optimizing the system for cost and performance, how to pick the right data types, how to pick the right compression types, and then how to use the tools to actually build out an ingestion and analytics based system. So this graphic will look similar. Will look familiar. We had a similar one in Dex yesterday, but this is kind of the again the backbone of the AWS data lake is built upon S3, and AWS has a whole heap of products and services that can integrate with this concept to allow administrators to build very complex and very efficient workloads. So there are some considerations to be made when putting data up on S3. The initial thought is to move files and data into a bucket, but what you'll notice will happen over time is that if you just kind of are continuously throwing data into just the bucket and the top layer of the bucket, you're going to run into performance issues eventually, just kind of stuffing a bucket full of data. Really, there needs to be a strategy for how to partition and set up the data. And on one hand, it's for performance reasons, being able, when you're scanning or crawling an S3 bucket full of data, if the data is not partitioned, you'll find you have to crawl the entire set of the data just to maybe just to read data out of one file, for example. Whereas if it's partitioned, you're working with a much smaller subset of data. So as a result, your queries will be faster, your storage costs will be less, your system will be more performant. And we're going to get more into detail in the next coming slides. But just know that these are kind of the main, high level things to take away. Like partitioning is important, the compression you use is important, and the tools that you use to manage, maintain these things are important. The hope is that you're utilizing AWS managed services for all of these data components, rather than trying to roll your own tools or do it yourself. Amazon has figured out a lot of the quirks of operating a system like this and really kind of distilled it into this Glue product. So let's talk about why partitioning is important. This is a kind of a simple example, but imagine this example expanded into scale, where we have potentially terabytes or petabytes of data filled in this bucket. And if it was just kind of a single flat directory with thousands or millions of files, trying to scan and issue queries and work with this data set is going to be very difficult and tedious. Essentially, what would happen is anytime I wanted to issue a query, I would need to scan the whole contents of this. In S3, it's not exactly a directory. It's a marker for like a folder type of object, but it's this similar result. Like we have a directory full of files, and it makes working with that type of system very difficult. Plus, you lose a lot of insights if it's all just kind of one big flat. Um, it's just a flat collection of files. You lose the ability to be able to parse things by year or by month or by day or hour. And depending on the data sets that you're ingesting, there's going to be different strategies for how you tag or partition the data. In this case, you'll notice that on the right side is kind of the partition version of this, where we're actually breaking out by date time, or like a date stamp, and then also further by country. So this gives us a couple pointers where we can then issue direct queries. If you look at this little red dotted line that's shown over on the left, it's kind of the whole contents of the bucket, and on the right, it's just the contents of that one folder, country equals US. So you can be much more granular when issuing queries. Which your queries will come back faster. You'll scan less data. It'll cost less to do. So all in all, like you need to have a partitioning strategy in place when setting up the data lake. So here's some real metrics. So filling a data lake with a bunch of data and then issuing a really simple select query to just get a count how many objects are in here. And you'll notice when comparing the non-partitioned to the partitions, there's a huge performance benefit. There's a huge cost benefit when the tools that are being used behind the scenes, just the way that they're operating. In a non-partitioned data set, it's got to crawl or scan the whole thing. And as that data set grows, so does that scanning time, so does the cost to do so. So it really is a necessity to have some sort of like partitioning strategy in place for the data lake. The next component is around compression. If you could imagine, things like log files and text data can really accumulate in size and get pretty large. And as these files grow, your queries, the scan time will grow. And really, there's a need for administrators to implement some sort of compression on top of the files that they're keeping in the data lake. Of course, there's pros and cons with each compression type that you pick, but the idea is you want to pick the right compression for the workload in mind, right? So it depends on if you're running algorithms on top of the data or just kind of doing analytics. You're definitely going to want to pick the right compression for the workload in mind. So here's an example, another kind of, here we got some stats and metrics to look at. So if we just had a text file, just a raw file, a .txt full of data, and it was about a terabyte in size, it would take about 4 minutes to like parse that file and scan through, and the cost would be like $5. Even though that's not very much money, you can imagine that at scale or like continuous processing, that's really going to add up. If we were to take that same file and change the file format and make it a Parquet file, and then use snappy compression on top of that, the size will come out to about 130 gigs. So that's 80%, almost 90% less than the raw text format. It'll scan through in about 7 seconds. That's 34 times faster. and then the amount of data scanned is going to be much, much less. 2.5 gigs as opposed to 1.15 terabytes. It costs a penny, right? So it's, you're scanning 99% less data, you're saving 99% more money. It's 34 times faster, and the file size on disk is almost 90% less. Like this is kind of a no-brainer. Like, throwing raw data on S3 for analytics, it works, but it's not the most efficient, not the most effective way to go. So operators are definitely going to want to evaluate using these different file formats, and assessing like not only this, but the type of compression that they're applying on top of it. So this adage has held true back from my IT days when doing migrations and whatnot and moving data around. Um, Not all data is equal or equivalent. If I had 100 gigs of consisting of 3 files, it's a different operation, like a file transfer operation, than 100 gigs of a million files. Right, so when there's many small files, you will see performance impacts. The more files there are, the more time it will take. The more requests that have to go through, more metadata that's involved. So in this type of system, fewer larger files are better than many smaller files. So we're going to get more into Glue specifically. So Glue is a really powerful AWS product, kind of a whole suite of analytics tooling. Started off very simply, and now it's grown into a whole kind of side. It's full of all sorts of features, and workflows and different like crawling capabilities. So it's very useful for administrators to like wrap up all their ETL and handle all the workflows and automation in one place. What we see a lot of times when customers are coming to us is a lot of homegrown stuff, right? So like homegrown, in-house built ETL jobs, they usually end up being just kind of hand coded and a little all over the place. And to an extent, it's good, right? Because you can hook those things into CI. The developers are usually very fluent and familiar with them. But it's also difficult to maintain. It's really error prone. It's laborious. So like somebody's going to have to be troubleshooting and really keeping a close eye on it. And anytime something changes on a remote side, some payload type changes or something, somebody's got to go in and make those adjustments. And it's kind of a never-ending thing. It's a full-time job. Somebody's going to have to stay up to date and just making sure that all the integrations are still, parsing and pulling the correct data, and that if changes do occur, you got to make those changes in your, ETL jobs normally, and like make adjustments to the system. So that's kind of the case for not rolling your own tool. You can certainly run any number of open source tools and components on your own compute. You can manage that yourself, but we wouldn't recommend it. We would recommend using Glue. So there's a few components to it, and I'm going to go over more in depth. But these are kind of the main ones: discover, develop, and deploy. So there's a component to Glue around discovery. So they call it crawlers. So you can run crawler jobs and point them at S3 buckets or Redshift data warehouse, or even like a relational database. And Glue can actually go look at that data set and query it, and it'll even try to apply a schema to what it's seeing, right? And so it'll make some educated guesses and go, hey, this looks like a string, this looks like an integer, this looks like a Boolean, and it's actually going to kind of map all the data and whatever you point it at, and create a schema on your behalf. Kind of behind the scenes, it's using a Hive format to collect and store all the metadata, and it's kind of like this database construct, and what's so powerful about it is that it hooks into several other AWS services, right? So the integrations are just really tightened on Glue, and the integrations allow operators to very quickly, get data up on AWS, very quickly crawl it and generate schemas, and then get right into doing, ETL operations and working with their data set to pretty much move it to any data store they want to run any ETL operation they need to. There's a whole like orchestration framework behind it. So these are some of the components kind of in the overview. We're going to talk about the data catalog first, kind of lined out in red there. So the data catalog, is kind of what I was referencing before. So there's the ability to maintain metadata for all the data that's discovered through Glue. You can maintain connections to any networked endpoints, like RDS instances and Redshift warehouses. Those have IP addresses. They're living in a VPC somewhere, and you need some network connectivity to get to those things. So you can maintain connections for those things. Things like Dynamo and S3 are more API driven. But you can still, have VPC endpoints for those and connections to maintain. And there's a whole, there's built-in classifications, and customers can even define their own. And one of the best things about this little system is that it allows for versioning. So even if your schemas are changing and the data that's going into that S3 bucket is evolving over time, uh, the metadata will be versioned with the data set as well, right? So you can constantly be evolving the schemas that you're putting into your data lake, and the catalog will just kind of get updated with it, and that allows you to, keep your data sets up to date, but still have some backwards compatibility to go look at past data sets. And of course, like one of the most powerful capabilities of this is the tie-ins, right? So this Glue data catalog component will tie in really nicely to these other AWS analytics services. So Glue ETL, we're going to talk more about, just another component of Glue. Athena, which is basically a way to issue SQL statements and query data that sits in S3, but using this data catalog. Redshift Spectrum is similar. It's for querying data in S3. And then EMR is more for like Hadoop and Spark-based workloads where, you can run these MapReduce jobs against data that sits in that data catalog. So the crawlers were what I was mentioned before around the automatic crawling and scanning. They can be run on demand or, at a scheduled interval. So it can be like event driven where, if this happens, then kick off a crawler, or it could be just scheduled once a day, once an hour, once a month. It depends on the workload in question and how often you're expecting that data to change. But through both on-demand and scheduled, operators have the ability to set up those crawlers in the way that they need them. So the crawlers will basically point at a given data source. They'll go try to extract the schemas. If it's an S3 bucket, it's going to look for the partitions that bucket is using, and it's going to try to detect a file type if it's looking at an S3 bucket. And there's a handful of built-in classifiers, and you can even build your own if you want to do something more custom. So that crawler can maintain connectivity to a few different data backends, right? So the networked resources I had mentioned, like RDS, that's going to be the open source databases, MySQL and MariaDB, Postgres, and Amazon's Aurora. For the warehouse, the crawler can also crawl data in Redshift, and there's a whole handful of formats that it supports out of the box, as well as like compression formats. This is a view of what it looks like in the console. This is a little bit older version of the console, but it'll look largely similar to this. This is from kicking off a crawler and having it crawl a data set in a bucket, and then updating schemas in a table based upon what it found. And there's a bunch of kind of metadata and just kind of details there, but we can see the table name is simple tweets JSON. In the analytics database, it's a JSON classified schema, and we've got a reference to the location from what specifically was crawled. There's no connection there because it's not a networked object. It's just an S3 bucket with no VPC endpoints or anything. And we can see in some of those tags there, compression type none, type of data is file, average record size is 456, I think, bytes, record count 1001. So there's a bunch of kind of like tag metadata that can be seen just in terms of like details about the crawler at the time it was executed or invoked. But then down below is the actual data that was pulled. So essentially, you can imagine a key value, like a dictionary, sitting in that file or object on S3, and it contains those keys and values, right? So entities is its own struct. It's like a little dictionary type, and we even get a little exploded view of the user struct, item 5 there. We can see contributors enabled is a Boolean, a description is a string, favorites count is an integer, right? So, and this is all, we didn't tell Glue, what anything was. We really just pointed it at a bucket, let it do its thing, and this is what it comes back with. So if you can imagine, right, we can really throw anything into this bucket, and Glue will do its best to pull schemas and tell us, what it's found. And if, say, for example, if I'm operating this system and I'm controlling the payloads that are being stored in our Glue sample data bucket, and I want to add some additional entries to my schema, I can just update them, right? And then the next time my Glue crawler runs, we'll see additional items appear below there, and Glue will make an educated guess as to what the data type is, which is very useful. So this version control thing is very powerful. So this is essentially anytime your schema is adjusting or changing, Glue will be able to tell you about it and tell you specifically what changed, right? So in my, I had given an example where I had added data to my schema, or like I updated what gets stored in the payload and stored into S3. But in this example, we're actually going to change one of the data types. So if you look at the tables below, you'll notice that between left and right, left being version 0 and the right side being version 1, if we look at the table below and we see the ID column and the data type is big integer, and we see in the table that that field was changed from our last run. So now that the Glue crawler has identified that that field has changed, it's going to tag a new version, and then it's going to change that data type to a string. Right. So even as we're changing just the data types within an existing payload that we're already storing, that's a versioning event. Glue will detect that, and you get a new version of your data catalog. And there's even a handy little checker thing, right? So it can tell you even who created this Glue crawler, or like what modified it. And, there's a record of everything that happens. So earlier in this in this deck, there was a slide around S3 and partitioning the data in there. And it was following a format which was like string equals XYZ. So this is pretty similar format where they're, in this example, we're doing month equals, the 3-letter identifier for the month, and date equals the integer for the day of the month. This is kind of a generic partitioning scheme. This kind of string equals X. This format, Glue can just kind of pick up automatically, and it'll pull in those specifics. Basically, before the equal sign is the column, and after the equal sign is like the actual data. So Glue will automatically pick up these partitions, in this format, and it'll, you'll be able to see and like visualize that in the console as you're working with Glue. You can pick data sets in any of these partitions and be able to crawl through, which in turn allows you to query across. All right, so the next component we're going to talk about is job authoring. So this is essentially picking from a data source that you have access to. It can be in your account, can be in another account, it could be just over the network. But these are the sources that that Glue can pick from, right? So S3, RDBMS, so MySQL, Postgres, anything on RDS, and Redshift and Dynamo. So this is kind of where we get more into the some of the ETL operations. So we're picking a source, and then we're going to pick a target, right? And that target can be another S3 bucket, it could be another database, it could be another Redshift warehouse. But this is where we start getting more into like, what does the output look like? Because in this, we're basically going to be able to take the data that we have found from that source and map it into the target or the destination. So we can pick and choose data. You'll notice anything with just a dash in the map to target row there, we're not taking with us. It's just not useful data. We don't really care to visualize it or see it or save it. It's just going to be extra data costs, so we'll leave it out. So in this case, we're shipping like 80% of the data in the source to our destination there. And so it goes, into more depth here, right? So we can customize the mappings as we're doing this process. So as we're bringing in the data, we can customize, however we want to then map those. And on the Glue side, it's going to generate, either Python or Scala code that we can use. And then there's typically like a trigger condition, right? So if we can have this kick off at a certain event, or we can kick it off manually. So most of the time when working with Glue, admins we write a lot of Python here at Mission, but Scala you're able to use Scala for working within Glue here. But Glue has Amazon's provided a Glue library for doing a lot of the data manipulation that you would need to do. And some of it is kind of standard or native libraries. So like PySpark, if you've ever used, you're able to use that within the Glue construct. Or you can even import your own custom ones, or just kind of use internal Amazon built ones. But it's intended to be collaborative. So, the hope is that there is an ecosystem built around these scripts and tools, and people share the tools and allow for code reuse. All right, so let's talk about the orchestration component. So in the past, operators would have to run this orchestration component themselves, right, on their own compute or on their own lambdas, however that they wanted to deploy it. But Glue actually has an orchestration built into it now, right? So you can do more schedule based, so just recurring. It could be every X hours, it could be at a specific time of day. But the idea is that it's scheduled and that it's going to get kicked off on a certain interval. Event-based is more, it won't do anything until you tell it. And typically there's some other event that'll trigger it. For example, when an object hits an S3 bucket, uh, kick off a glue job. There's a whole host of events that you can program, um, but essentially, right, you can tie any number of triggers into glue to be able to kick off jobs. And because it's a managed service, it's integrated really tightly with other Amazon services like CloudWatch, where we do monitoring, for example. So things like logs and alarms can all be set up through CloudWatch for glue. So job bookmarks is a feature or functionality that allows administrators to basically save the state of their glue jobs or runs. So rather than restarting right from a certain point and making the glue job process a bunch of data that maybe it already has, you have the ability to kind of pick up and resume where you left off. So it's a lot more efficient than just kind of starting a job and letting it do everything from scratch, even if it already has. So as mentioned, Glue, it really is tightly integrated with other AWS services. And in this specific slide, it's talking more about your ability to monitor your jobs. So a Glue job can emit metrics that you can then see in CloudWatch and alert and alarm upon. So helpful for administrators who want to have some sense of the health and status of their jobs, right? So you can tie in notifications to alert when something has gone wrong. And if something has gone wrong, there are lots of logs to show for. So by default, Glue is going to be tracking the entirety of logs for the whole run, but they'll also parse and just kind of take the error logs out of the main logs and put them into its own error logs list for review. So as jobs are running, you can see all the logs that they're generating and then go view any errors if they produced any. So CloudWatch, the reason I bring up CloudWatch so much, because part of the events and the triggers behind it are a lot of times done through CloudWatch, right? There's some CloudWatch rules that you can set up for like the scheduled based jobs, and then there's CloudWatch events that you can use for triggering glue jobs. So CloudWatch is a pretty integral part to all glue deployments. And usually if you're using glue, you're using CloudWatch. So another great thing about how Glue handles the job execution is that it's serverless. You don't have to have any compute. You don't have to have an auto scaling group that you're bumping up the instances and letting it scale up for. You don't have to do any of the provisioning or management of servers and machines. You really just supply, code that needs to run and instructions for the orchestration behind the scenes, and Glue is doing that in some serverless way. In this case, what it really means is Amazon is providing the compute, right? They're spinning up the workers that your Glue job needs, but it's invisible to the user, right? So you kind of just set the criteria, and Amazon will spin up workers in the background to do the job and go through and do the workflows and whatever. And like everything else on AWS, it's all pay as you go. So you're only paying for, while things are running and like actively processing, so while consuming them. With this, there is a certain amount of tuning, right? So there are different like sizing and capacities that can be specified. So there's, in in all AWS services, there's the ability for financial levers and tuning and whatnot, and Glue is no different. So this is what an end-to-end Glue workflow might look like. Starting with a data store. Let's say that is a MySQL database on RDS. So step one is always to crawl the data. So a Glue crawler can be kicked off to go parse the data in that database and generate schemas in the data catalog. Next, we create the desired targets. Where do we want this data to go or to live? So that'll be something like Redshift or S3. Next is more on the ETL side. So we generate and prepare any ETL. Usually there's a lot of customization that happens here. Additional data processing and number crunching. Anything to kind of build out the data that is getting passed down to these target systems for anything useful for reporting or visualization. And then it's just a matter of executing jobs and on some interval and continuously pulling data from that source system through the pipeline and into the target system. And there's always a good amount of tuning and configuration and customization that comes with all this. So let's talk about some other features that are useful for administrators. This Python shell job is a component to Glue, which allows administrators to basically go into like an ad hoc session where they can evaluate their scripts and test things out. But you can also like interact with the system through this way as well. So it's because of the nature of it, it's very simple. It's really intended for small or medium tasks. If you need something larger, more complex, you're going to want to go through like the Glue proper, like set up a full job. I'll touch on this thing. So there are a handful of transformations that Glue can provide out of the box. This one in particular is called find matches. So the intention behind this transformation is to be able to find like related products, place a supplier. This kind of the meta it's listing there, but it's basically finding similarities in the data set. One of the use cases is around like fraud detection or identifying duplicate accounts or duplicate items. So it can be used for a lot of different use cases, and it's just a built-in component that customers can leverage using Glue. All right, last section on Glue is around the workflow. So of all the things that we've seen so far, Glue can essentially visualize, what your workflow looks like, and it can report on the status of this whole workflow as it's progressing, right? So these, I'm sure you can imagine, can be very complex. Many things can run in parallel, things can run in series, things can fork and branch and go all over the place. These can get very complex. And this workflow visualization is really useful for administrators to get a sense of the overall workflow. It can be different from when you're in the console or in a shell configuring some workflows to kind of the outcome or the what has been produced from that activity. So this is useful to see from like operational perspective, like so everybody has a sense of what the workflow looks like, but also for like monitoring and maintenance, right? Having that insight into the overall workflow is really important. And so let's look at an example of an event-driven workflow, right? So in this event-driven workflow, it's going to be triggered by new data hitting a bucket. So, we've got an S3 bucket. Let's say some new data has arrived in that bucket. S3 has triggers built in. So anytime there's a new object placed, it can invoke a Lambda function on your behalf. In this case, data can hit that bucket, a Lambda function gets triggered, which then calls our glue crawler. That crawler can then go crawl the new data set that's sitting on S3 and then run a series of jobs or like a workflow behind the scenes. In this example, it's real simple. We're just going to run our optimized job. So that will essentially go parse and perform some ETL on the data in our new raw bucket. And then move it into a new optimized bucket, right? So we're like generating a new data set based on the raw data that hit S3. When that's done, we're essentially ready for reporting. Our new data is in the bucket, and our visualization tools can pick it up. So this is what an event-driven workflow might look like. Something happened, so we trigger Glue to run a crawler, to run a job, and to output all the data that's generated into a new storage component. Oh, I thought I had a time. Well, in the alternative from an event-driven workflow, and it's more scheduled, it's largely the same. It's just that rather than when data hits a bucket, it'll be on an interval. At this time, crawl the data set, run the optimized job, all through the steps, largely similar, just how it gets invoked is a little different. I have not been checking the questions. I've been doing my slide. If there's any questions, feel free to throw them in, because otherwise we're done with this content. I'm going to be going through Glue in the labs. I've got some labs scheduled for later where we're going to be doing some activities with Glue, and we'll be working with QuickSight, Amazon's visualization tool, and we're going to be able to crawl some data in S3 with Glue, output it into another bucket, and kind of clean up that data set, and then visualize it with QuickSight. I'm really excited to go through that lab with everybody. But think of any questions, throw them in the chat. Let me know what's on your mind. Otherwise, I'm going to plan to, let me stop sharing here. Who's up? Will, are you up? It looks like you're primed.
I am up, yes. Thanks so much, Lance.
Awesome. I'm going to pass it over to Will, and I'll see you guys here in a bit.
Okay, cool. Thanks so much, Lance. So, as y'all might have guessed, the next lab is going to be all on Glue. So we're going to do this the same format that we did yesterday, which is, everybody should have the link to the lab, which is a public-facing link for the lab walkthroughs. If you don't have that, then we can certainly post it in the chat as well. As we mentioned yesterday, the labs that were done yesterday, the labs that we're doing today have dependencies on those labs. So if you weren't able to do the labs yesterday, you won't be able to just kind of pick up with the labs today, and you may need to kind of start from the beginning. So if that's the case, not to worry. I also mentioned yesterday in the chat that your lab environments are going to be available for 3 days total. So you'll have access to the lab environments until Thursday around like noon Central Time. So if you're not able to get through these labs during this event or whatever, don't worry about that too much. You should have plenty of time to run through them. So yeah, this next lab is going to be all about Glue, and as Lance mentioned, Glue is sort of like a middleman in this case. So yesterday the work we did was getting our raw data into our data lake, right, using DMS, and this lab that we're doing now is going to be using Glue to create our crawler, do some cataloging, some compression, reformatting of data, and then later today, we're going to be using Athena and QuickSight, which Lance mentioned, to do some querying and visualization on our data, which is, the really cool stuff. That's the whole point, right? Doing actual analytics on our raw data. So I'll let y'all go ahead and do that. We're going to post the link to the lab. Actually, I'll post it right now, just in case anybody needs it. There's a link in case anybody needs the walkthrough. And as you'll notice, when you look at that, there is one mandatory step for this lab, which is just the first one. There are 2 optional steps. If you're able to complete those, I would definitely do that. It'll be useful for you to see. If you're not able to do those, that's not a big deal. Just completing that first step will build all the dependencies that you need for the following labs later today. So again, if anybody has any questions, feel free to pop them into the chat, and we'll be here for the next half an hour or so, 40 minutes to do this. And just let us know if you have any questions. Thanks. All right, y'all, I wanted to pop back on for 1 second, just to make sure that everybody could kind of see what I was talking about because I wasn't sharing my screen. So this is the lab we're going to be doing right now, transforming data with glue. You know, if you'll step through this, it's fairly simple. One thing that I would call out on this is make sure that you pay special attention to the file names and S3 bucket locations and things like that that are in this lab, because as Lance also mentioned, the data cataloging process is highly dependent on the structure of the raw data, right? So that's sort of like, it can be seen as like a folder structure. That's super important for the catalog process to run correctly, and then for all of our downstream processes that have dependencies on it to run properly. So just make sure that you're keeping an eye on that. And you'll see here at the very top too, you know, there's an overall architecture diagram. So this stuff that we did yesterday is kind of here, right, on the left. And then what we're doing in this lab is all this glue stuff here. So we're going to be doing 2 crawlers, making a glue data catalog. And then in our labs later today, we're going to get down to the actual kind of like downstream analytics stack, which is QuickSight, our visualization tool, and also Athena, which is our serverless query engine. So yeah, just step through this. And if anybody has any questions, let us know. Thanks.
All right, hey folks, I think it is about time to get started with our next section. I think we had a couple of follow-up questions that we're getting answered on the chat right now. But if there are any other questions from this lab, feel free to get to us in the chat, and my peers will get to you. Thanks. Okay, just confirming, can everybody see my screen where it says consuming the data lake?
Yes.
Perfect, thanks, Melissa. All right, awesome. So with that, we'll get started. So hi, everyone. My name is Banerjee. I think I've mentioned before, I'm a solutions architect at AWS. I'll be guiding you through the next section. So we previously talked about what a data lake is, how to hydrate it, transform it, work with it. And really now we're going to talk a little bit further about how to explore some of the possibilities and patterns for making the best use of your data lake. So let's start with what not to do, right? So in earlier times, we talked a little bit about this earlier, but due to the restrictions of storage and compute in traditional data centers, the relational database was often the only place that reportable data really lived. So with the advent of data warehouses and data lakes, this has really become more of an anti-pattern because relational databases, right, we don't want to use them to accommodate all the different kinds of data and queries that our businesses need to serve, right? So we know that that's true, but and some of you may not be surprised to find this out as well, but just creating a data lake doesn't solve that problem. So it alleviates some of the problems, right? You can support different data formats, volumes, and velocities, but it's also not always the best place to directly query your data, right? So traditional on-premises solutions for data storage, data management, and analytics can't really keep pace with that. Data silos that really aren't built to work well together, they make it difficult to consolidate data to perform comprehensive and efficient analytics. And that's really going to limit your ability to get more insight and value from the data. And there's no one tool, right, that can do everything. You need to use the right tool for the right job. And we've been talking a little bit about purpose-built data stores and services that can enable you to build more of that configurable big data architecture, right, to meet your specific needs. But business problems are really far too wide and complex for one tool to solve everything. So if there's one takeaway, that's especially true in the big data and the analytics space, right? So at a broad, very high level, right, we've talked a lot about how there's a broad selection of analytics services that kind of can fit your data analytics needs. But let's talk a little bit about segment by segment, layer by layer, what that looks like, just for 1 second before we dive a little deeper. So there's data movement, right? There's data storage, and then there's data lakes to big data analytics, machine learning, and anything in between. So for all of those different services, you want to target the best price, performance, and scalability profile for your use case, right? And we've already explored some of those, like database migration service, Glue, right? We just went through Kinesis and S3, of course, right? So using these tools to approach a modern data architecture is going to allow you to rapidly build scalable data lakes and use a broad and deep collection of services to gain insights while ensuring compliance, ensuring that things are staying put when they need to and moving around only when you want them to move, right? Making sure that folks that are wanting to access data are only able to do so if they should be able to, and doing it at scale. So all that's great, but where do you start, right? So the first step is understanding and mapping your data in terms of structure, in terms of access patterns, and other characteristics of your data, right? Things that you can categorize and put into buckets. The other two steps are about learning about your consumers and then choosing the right tool for the right job. So let's dive in. So this chart, at first is a little overwhelming, but it's just going to help us map, how to understand data. So the first characteristic is how structured is your data, right? Does it adhere to a specific well-formed schema? Is it the case that, are you running Apache are you storing Apache web logs? Is it standardized data protocols that you're working with, contractual interfaces, or is it completely arbitrary binary data, right? We see this with images, audio, video, PDF documents, or is it, semi-structured, somewhere in between with a general structure, but with potentially high variability across each record, as is the case with JSON or CSV data. So the second characteristic is how quickly new data needs to be available for querying, and we refer to that as the temperature, right? So is it the case that you have a real-time scenario where decisions have to be made as soon as new records are coming in, right? With campaign managers maybe making adjustments on conversion rates, or a website that's making product recommendations based on user behavior similarity, right? Or is it a daily, weekly, monthly batch scenario, such as maybe in the case of model training or financial statement preparation or product performance reporting, or maybe it's somewhere in between again, right? Somewhere in between, like with user engagement emails, where it doesn't really require real-time action, but you can really have a few minutes or even a few hours buffer between the user action and the touch point itself, right? And then the third characteristic is the size of the data ingest, right? Is it record by record as data is coming in? So like with JSON payloads from REST APIs that maybe are measuring a few kilobytes at best, or is it a large batch of records arriving all at once, maybe, such as with systems integrations and third-party data feeds, right? Again, it's somewhere in between for a lot of our customers, right? Where maybe they have few micro batches of clickstream data, right, aggregated together, stitched together for more efficient processing. And then there's the fourth characteristic, which is the total volume of your data, and also its growth rate, right? Because we have folks that are in the realms of gigabytes and terabytes here, or we have folks that are intending to store petabytes or even exabytes, right? We talked about Epic Games before. So how much of this data is required, right, for your specific analytics use cases? Do you need to burn through all of it, right? Do the majority of your queries only require maybe a certain rolling window of time? Or do you need a mechanism to query the entirety of that historical data set? So the fifth characteristic, and the next one is what type of cost profile are you looking for? What the cost is going to be to store and query that data in any particular location, right? When it comes to any sort of computing environment, generally we see a triangle of constraints, right? It's easy to visualize that way between a couple of important, key performance indicators like performance, resiliency, and the cost, right? And the better the performance and the higher the resilience that you want your storage to have, typically the more expensive it tends to be, right? You may wish to have very fast queries over petabytes of data, which is the kind of environment that a really modern data warehouse can provide, as an example. But maybe you decide to settle on querying terabytes of data compressed in open source format like Parquet using Athena in order to meet your cost requirements, right? And then finally, what is the type of analytics queries, right, that you're going to be running against those data? Is it going to be a dashboard maybe with a fixed set of metrics, right, a drill down? Or is it the case that you're going to be participating in maybe larger numerical aggregations that are going to be rolled up by various business dimensions, or maybe it's going to be used for diagnostics, like leveraging string tokenizations for full text searching and pattern analysis. So we come at it from a frame of mind of you need to first understand what your data is, right? What you're planning to do with that data, and how do you want it to be visualized or consumed, rather, right? So a modern approach acknowledges that idea that taking a one-size-fits-all approach to data and analytics eventually is going to lead to compromising, right? So it's not simply about creating a data lake or integrating with a data warehouse. It's not any of those individual things. It's about actually integrating a data lake and integrating to a data warehouse and having purpose-built data stores, right? And being able to unify governance and easy data movement. And it's a worthy challenge, right? So with the modern data architecture on AWS, we enable you to store that data in a data lake and then use a ring of purpose-built data services around that lake that allows you to make decisions with that speed and agility that you want without having to burn through a lot of overhead trying to figure out how to manage this at scale, right? And just a few examples, right? So very hot data that you may have may need to be stored and processed in memory. So caches or in-memory databases like Redis are typically appropriate for that, right? So AWS offers the ElastiCache service. So that provides you a managed Redis or a Memcached environment. Similarly, you got NoSQL databases, and those are ideal when you're facing high velocity but smaller size records that are accessed along maybe known partition values, right? So for that, we offer DynamoDB, and DynamoDB is both highly scalable and elastic. So there's no limit to the amount of data that you can actually store in a DynamoDB table, and the service sort of automatically allocates more storage as you store more data using the DynamoDB write API operations. So that service is basically, it's elastic in the sense that you can simply dial up or dial down the read and write capacity of a table as your needs change. And then there's general binary or object storage, which is appropriate for files that are unstructured and not indexable or otherwise opaque to the business without specialized tools that really understand their format. And if you plan on storing anything larger or really greater than 400 KB, blob data like digital video, images, or music, you'll want to consider Amazon S3, of course. DynamoDB can still be used in this scenario for keeping track of the metadata like the item name, the size, the date, the created owner, location, so on about your binary objects. And we've already focused quite heavily on S3 as that platform for the larger data lake, right? It has a number of features that also further extended support for analytics use cases. But search engines, right? So also search engines work well for warm data that can be queried in perhaps an ad hoc fashion across any number of attributes, including like string tokens, like I was mentioning, right? So Elasticsearch, right, is a very popular search engine. So AWS offers the Amazon OpenSearch service, which is the successor to the Elasticsearch service. And OpenSearch offers broad compatibility with Elasticsearch OSS 7.10, and that was the final open source version of that software. And then lastly, you've got data warehouses, which provide like I was mentioning, fast aggregation capability over a large amount of structured data. So with Redshift, you can query and combine exabytes of structured and semi-structured data. And you can do that across your data warehouse and your operational database and the data analytics, data lake using standard SQL. So Redshift really lets you easily save the results of those queries back to S3 as well, using open formats like Parquet so that you can do additional analytics from other services after you're done, like EMR, right, Athena, and SageMaker. So with these technologies, while technologies like Redshift are designed to execute and sort of aggregate complex queries and quickly, they're not really optimized for high volumes of concurrent writes. So when data needs to be loaded in batches, you really don't want to leverage a warehouse because warehouses are prevented from being able to serve real-time insights over hot data. So those are just a few of the considerations that you want to get into when you're trying to understand your data, right? Before you even jump into the next challenge, which is understanding your audience. Give me just 2 seconds here. So speaking of audience, right? Who is your audience? We're taking a stab at understanding our data, and of course we can spend a lot more time at just understanding data per use case for business, right? But the next step is looking at our consumers and how to better serve their needs, right? So let's talk a little bit about how we can identify folks by user profile, by a persona, and be able to better understand the needs of our business users so that we can then match those. So as tasks or projects across your business grow, we see that it's typically useful to have defined personas when you're engaging in those activities to help align needs and priorities to stakeholders. So we encounter a lot of customers who have recently maybe retired or are on their way to retiring their on-premises data center, and then they're trying to move their entire IT environment to AWS, perhaps even in one fell swoop or as part of a phased approach. And as part of that move to AWS, a lot of customers will migrate or build from scratch a lot of the analytics pipeline, which is a noteworthy task in and of itself, right? Excuse me. And that's a pretty massive task in and of itself, right? So as a result, they start to say, okay, we want to run a more efficient and profitable business, so we want to leverage all the data at our disposal. And if we're going to do that, then we need to also leverage our use of data science and AI ML, and also help solve these difficult optimization problems. It's a lot to take on, right? So at the same time, they also have a very small team, perhaps, to help them optimize their business operations and minimize costs and maximize their profitability. So a lot of those responsibilities really start to overlap, and it can become challenging to keep a mental model of user needs. So there's a number of personas, but I'll elaborate on just a couple in particular. So data scientists, for example, they're responsible for leveraging and really discovering insights from massive amounts of structured data and unstructured data to help shape or meet a specific business need or goal, right? And most data scientists are actually, in reality, spending 80% of their time finding, cleaning, and reorganizing huge amounts of company data, looking for business opportunities and optimizations that are really hidden within the data itself, really, the subtext, right? So those folks are comfortable with statistics, machine learning frameworks, data science tools such as R, basic programming in Python, big data tools such as Spark, PySpark and Scala, right, and SQL. And they may typically also be fans of ML notebooks like Zeppelin or Jupyter. And typical use cases for those data scientists in AWS looks like analyzing, again, large volumes of data, maybe perhaps from Redshift, right, and your S3 data lake. And to do this, they need to have ease of access to that raw data and the flexibility to create data model, ingest data, run algorithms, all of that stuff, right? The data model also needs to be temporary and iterative in nature because they're going to be flexible. And for these folks, AWS services like Glue and Redshift can really simplify that process of data wrangling, and it helps you really clean up and prepare your data quickly and cost efficiently. Then there's the data engineer, right? Just a few bits on the data engineer, right? These are people that are really going to be building the ingestion pipeline and who are going to be spending most of their time ingesting data into the data lake for their analysts and their scientists to use. And so these folks may be experts, again, with similar tools like Python, Spark, and SQL, also ETL tools, right? And it's critical for these engineers to be able to quickly turn asks from the business into a reality, to be able to better help those users at the end of the day get to that, the downstream use cases faster, like data scientists and everybody else that's going down that chain. So how do you go about leveraging AWS to build a pipeline that addresses each of those personas, right? So here's a brief glimpse. We'll talk a little bit more about architectures in a second, but here's a brief glimpse at what that might look like. So envision a data platform analytics architecture as a stack, right, of several layers or as a process workflow. And so first, you're really bringing in data into your data platform and your data lineage lifecycle view, and you're ingesting data into your storage layer. This is your structured and unstructured data. And then you'll have a layer to store your business and technical metadata about your data sets in the storage layer, and this is where your data processing kicks in. And then at that consumption step later on down the pipeline, you'll be able to enable those user personas that we're talking about to do purpose-built analytics while protecting your data across layers from unwanted access. So a combination of fine-grained access control and being able to give people services they need to get their jobs done quicker at the end of the day, whether it's through event-triggered workflows or cron jobs, and refreshing data at the pace that the business needs it, per use case. That's the aim and the goal here. So in the next few slides, I'll talk a little bit about just a number of sort of use cases like dashboarding, ad hoc analysis and reporting, as well as machine learning, and just talk a little bit through available services and the architecture patterns that we see best help those customers succeed. So we're going to dive into developing data services for enterprise data warehouse users, using Redshift to get BI, using building user-friendly dashboards for your business users, and also quickly querying any transform data for your IT users. And also we'll talk a little bit at the end about how your data scientists can also utilize AWS to clean and normalize data for machine learning models. So the first sort of order of business, right, is dashboards. And what are dashboards? At the end of the day, at a very abstract level, they're a visual representation of a given key metric or set of metrics, right, that change over time. So they typically intend to quickly inform human beings, business users of the overall state of a given system when there are many complex moving parts so that they can do their jobs in a faster, safer, more efficient way. So most dashboards are going to be using a fast polling loop against a backend data store with caching for near real-time visualization. And then there's another approach, which is to use PubSub with something like WebSockets, perhaps, into an underlying data stream. So because of their real-time nature, dashboard data tends to be hot, and the records are small in size typically. And as such, partitioning the metrics aligned to your dashboard views and storing in DynamoDB is a pretty common approach that we see, actually, right? And speaking of DynamoDB, let's talk a little bit about architectures that support that. So take a look at this visual. So let me break that down by components. So in the middle, we have DynamoDB, right? So DynamoDB is ideal for storing real-time hot data that's frequently accessed. To run real-time fast lookup against DynamoDB, you would design the table schema based on the reporting requirements and the access patterns. For example, if you need to do real-time reporting of your invoice transactions, you can access invoice or transaction data from a DynamoDB table directly by using the query or the get item API calls. So you design your schema with an appropriate partition key or partition and sort key for query purposes. So you may ask, well, okay, well, how do I run analytical queries against data that's stored in DynamoDB? So it depends, right? For low frequency use cases, you can actually use something like Athena's federated query or Amazon EMR with HiveQL to query directly against that live DynamoDB data using SQL-like statements. But you can also, additionally create local secondary indexes and global secondary indexes within DynamoDB to support queries using different attributes against the table. But DynamoDB is really, at the end of the day, optimized for heavy online transactional use case at scale, where the majority of the data operations are expected to be fully indexed and materialized to avoid any variability in performance. So then, how would you do something complex like freeform, text searches in DynamoDB? For example, let's assume that we have a table like an invoice transactions table, and it contains an attribute like invoice doc as a map data type to store like a JSON document. Well, how do you filter the particular client transaction or query the data? Well, like for example, like the quantity for printers or desktops or tricky vendor names, etc. How do you handle that within the attribute stored as a document in DynamoDB? It goes back to choosing the right tool for the right job. So DynamoDB is not suitable for free text search against large volumes of data. For that, we recommend OpenSearch Service to address those kinds of requirements. And with Managed OpenSearch Service, you're getting all of your desired querying capabilities that we were talking about earlier. And then, of course, if you wish to enable dimensional reporting within a dashboard or cross-referencing operations, again, a very common pattern is to set up a forwarding process for our data from DynamoDB to OpenSearch via Lambda. And we can load streaming data into OpenSearch, into an OpenSearch domain from many different sources. So for large data volumes, we recommend using something like Kinesis Data Firehouse, which is a fully managed service like we talked about that automatically scales to match the throughput of your data and requires no ongoing administration. You can also transform, batch, and compress the data before loading it too. Right, so you can leverage the streaming functionality to send the changes to OpenSearch via a Firehouse delivery stream. And before you load the data into OpenSearch, you may actually want to perform transforms on the data, transformations, right? And so you can use Lambda functions to perform that. So in this case, you would maybe subscribe a Lambda function into a DynamoDB stream, publish that to Kinesis Firehouse, right? And then perform one final Lambda transform before maybe flushing the results out to OpenSearch. And for a real-time streaming dashboard, you can also have Spark streaming on EMR, read it from a Kinesis stream, transform that data as you need it, and then you output the results to DynamoDB. For OpenSearch, we also, the service itself offers visualization capabilities that are powered by OpenSearch dashboards and Kibana as well. So we talked a little bit about using, this DynamoDB stream-based pattern. Let's take a look at another pattern and that is doing real-time visualizations in an event-driven way. So an event-driven pipeline, to be specific. So assume that, let's say, for instance, a data analyst builds products reviews reports for the business users from your data lake, and they use BI tools like QuickSight for visualizing the data. So they use the reports to evaluate the product reviews, the star ratings, right? And that helps them plan new product offerings. So because these reports are gaining in popularity, an analyst in a business typically may reach out to a data engineer and say, hey, is there any way to make these reports perform faster, save costs? So to accomplish that, the engineer may decide to build a data pipeline that so that these reports can really be loaded from a lake into Redshift's attached storage, so that QuickSight maybe can reflect the visuals much more quickly, right? So in practice, this would mean building something like what you're seeing on screen. So a data pipeline that sources the data and then performs ETL operations and then populates targets. So for the ETL job, of course, you can use S3 as your primary data store, right? Data lands in the S3 bucket, and we refer to that as the raw zone. And then as the new data flows into the lake, an S3 trigger that's configured on the bucket triggers an AWS Lambda function, which starts Glue ETL jobs. And these jobs can process the raw data and load and output the process data into target data stores like Redshift or a process zone S3 bucket. An example of an ETL job would be converting the data to Apache Parquet format and then storing it in the processed S3 bucket, for example, right? So you can use ETL jobs to achieve other objectives too, like more granular partitioning, compression, or enriching the data as well. So the Glue data catalog, I think we talked about this earlier in a presentation, stores the metadata in the QuickSight datasets that are created using Amazon Athena data sources. And Athena is an interactive query service that makes it really very easy to analyze data directly in S3 using standard SQL, just for reference, right? So to provide fast access at the end to data sets, QuickSight actually provides you a fully managed calculation engine. We call that SPICE. It stands for Superfast Parallel In-Memory Calculation Engine. And to trigger the SPICE dataset refresh, after those Glue ETL jobs we talked about, they finish, CloudWatch can trigger a Lambda function that initiates the refresh. And this pipeline essentially transforms your data, updates the QuickSight SPICE datasets after completion, and after the data is imported into SPICE, you can simply create visuals, as you normally would to display the data. So using an event-driven architecture to automate the refresh of your SPICE datasets, at the end of the day, really make sure that your business analysts, the ones that are reporting, are always viewing the latest available data. So this reduction in time to your analysis can actually help your business get to those insights quicker without having to wait for a manual or scheduled process. Additionally, when you're only refreshing SPICE when new data is available, that way the underlying data storage resources are actually being used more efficiently, so that you're actually only paying for what you need. You're not constantly refreshing. So that was a little bit on the idea of using real-time visualization using an event-driven pipeline. Let's talk a little bit about the next category, really, which is reports. So reports are different from dashboards in that they're typically a static representation of data rendered at a point in time, right? So this data tends to be perhaps too varied or complex to adequately represent in a summarized sort of dashboard, right? So it's also useful to compare generated reports side by side, A/B, to see how time has influenced the results as well. Because report rendering is typically an offline process, that data typically has a colder temperature. So if you have highly relational data requiring multiple table joins, then an offline relational database is still a valid option on the table. But highly connected data requiring traversals beyond just a few table joins, like social graphs or user behavior data, would really be better landed in perhaps even a graph database like Neptune, which we're not talking about in this immersion day or in this workshop specifically. But if your reports require numerical calculation against very large volumes of records, then you'll want to then consider a column-oriented database like Redshift. And another option, perhaps, is to query your data lake directly using Athena, which is storing the data in a highly efficient sort of column-oriented file format like Parquet, right? And then, with each of these options, you'll really want to make sure that you're ensuring compatibility with your report rendering tool of choice. So we offer QuickSight. So this is another sort of example of how you can leverage Redshift in the perhaps existing analytics pipeline that you may have. So here you can see that Redshift's actually being used to store business data in Redshift instead of keeping all of your data in Redshift and keeping the rest of it in your lake. And so with with Redshift's most recent updates to RA3 instances, you actually have access to managed storage within Redshift. So you can choose the number of nodes based on your performance requirements, and then pay only for the managed storage that you use. And then on top of that, only populate that storage with data that you really need to keep in your data warehouse. So Glue provides comprehensive data integration capabilities between all these services, right, as the name would imply, that make it easy to discover, prepare, and combine. And then Redshift can easily query data in your S3 data lake as well. In fact, Redshift and Athena both support federated queries, which gives you the ability to run queries across data stored not just in your data lake, but in your operational databases, your data warehouses, and your data lakes, right, to provide that multi-panel sort of multi-data source view with no data movement and no setup to maintain complex ETL pipelines, right? And one of those most important pieces of having a modern analytics architecture is the ability for you to do all of that at scale. And also a secondary priority is to authorize and manage and audit access to data. In fact, security itself could be considered a job zero, right? It's the first priority. So while you're creating this entire modern pipeline, you want to make sure you're doing that at scale, but not only are you doing that at scale, you're managing security. So this can be challenging though, right? Because managing security, access control, and audit trails across all of the data stores in your organization is complex, it's time consuming, it's error prone. So that's where lake formation can fit in, right? And so lake formation actually provides you the central catalog to store and manage data, manage metadata for all the data sets hosted in the data lake using the Glue data catalog. So services like Glue, Athena, EMR natively integrate with lake formation, and they automate discovering and registering those data sets, those metadata data sets into the lake formation catalog. So let's move on to one of the last categories we'll cover, which is ad hoc analysis. And with ad hoc analysis, we're typically really referring to operations that are only performed when the intended insights are already well established ahead of time, or the information that's sought after is on a one-off basis. So with that, your data store typically needs to have support for a robust querying language across a wide range of indeterminate functions, right? So for example, an analyst may leverage sampling functions to derive a baseline and then calculate the deviation for each data point to find anomalies. Or a data scientist may decide to use stochastics to understand the variability of your data sets. Even support and operations engineers can use things like pattern matching and similarity functions to search through application logs when they're diagnosing a system error. So in those situations, the data will either be medium or cold temperature, and the record size and the total size can totally vary based on the business context. And relational databases there could provide SQL support, but they tend to be limited in the breadth of functions and the algorithms that are provided. So for those use cases, when you're integrating ad hoc analysis with reporting, as with reporting, Redshift and Neptune are good ad hoc analysis environments if you're exploring numerical aggregations or highly connected data, respectively. For loading, data into Redshift itself, best practice is to actually also leverage the Redshift's copy command rather than performing individual inserts into those Redshift tables. That actually allows you to optimize the load operation for Redshift and prevent the need for lots of small transactions that can impact the health of the cluster. You can also use things like Redshift Spectrum, right? You can actually efficiently query and retrieve structured and semi-structured data from those files in S3 without having to load the data into Redshift tables. And what Redshift Spectrum does is it basically employs massive parallelism to execute very fast against large data sets. Most of the processing actually occurs in the spectrum layer, the Redshift spectrum layer, but most of the data remains in S3. So multiple clusters can concurrently query the same data set in S3 without the need to make copies of the data for each cluster. Athena is also a good option here. So if the analysis is only occasional and it doesn't require a full-time Redshift cluster, right? For more advanced analytics, such as like stochastic analysis that I was talking about earlier, R is very common, but it's restricted to like a single compute environment. To get the benefit of distributed computing, we see folks leveraging Spark on EMR, which is extremely popular with its support for both SQL over data frames and Python or Scala algorithms running over RDDs. So both of those offerings can be integrated into your existing pipeline. So that's what the architecture here is intended to represent. Now we're running a little tight on time, so I'll move along a little bit quickly through these next few slides. But yeah, this is another visual representation about ad hoc analysis. So of course, again, after ingestion, you're starting with cataloging first, right? So you can't really make use of your data after ingestion unless you catalog. So the Glue data catalog gives you those references to data that are sources for your ETL operations. And then typically you run a crawler to take inventory of the data in your data stores. But there's other ways to add metadata into your data catalog. So right, a crawler can crawl multiple data stores in a single run. And then once it's done, it creates or updates one or more tables in your data catalog. And then ETL jobs that you define in Glue use these data catalog tables as sources and targets. And the ETL job reads from and writes to the data stores that are specified in the source and target data catalog tables. Again, here's where as part of this flow, lake formation actually comes in and allows you to define and enforce access policies when using Athena queries to read data stored in S3. And lake formation gives you, the authorization and governance there. And then you can use Athena to query both data that is registered with lake formation and also data that's not registered with lake formation as well. And with a few actions in the management console, you can actually point Athena at your external tables through the data catalog, accessing data in S3, and then start using standard SQL to run ad hoc queries and get results in seconds. And we'll see that in the next lab. So Athena, by the way, is serverless, right? So there's no infrastructure to set up or manage. You really only pay for the queries that you run, and it scales automatically. And it's also running queries in parallel. And so the results are fast, even with larger data sets and complex queries. Now, the last topic we'll cover today in the consumption module is talking about machine learning. So how you can leverage ML with AWS in your existing pipeline. So we talked a little bit about Zeppelin and Jupyter. So speaking of Zeppelin and Jupyter, there's those are the most common environments for data engineers that are doing data discovery, cleansing, enrichment, labeling, and preparation for machine learning or ML model training. So Spark provides the Spark ML library, right? That contains implementations of many common high-level algorithms like regressions, PageRank, K-means, and many more. For algorithms that leverage neural networks, data scientists will be using frameworks like TensorFlow or MXNet, or higher-level abstractions like Keras or Gluon or PyTorch. And those frameworks and common algorithms can be found in the SageMaker service, which provides you a full ML model deployment, development, training, and hosting environment. And data scientists will leverage the managed Jupyter environment within SageMaker to do data preparation. Typically, they'll set up a model training cluster with a few configuration settings, start their training job, and when they complete, they can one-click deploy that model and begin serving inferences over HTTP. So the ML model development is performed almost exclusively, these days on files and HDFS. So querying the S3 data lake using SageMaker directly is actually the perfect fit for a lot of these activities. And you'll see that in the next visual, along with a couple of other AI services that we offer alongside SageMaker. So just an example here, right? So you can copy query results for sales of products in a given region from maybe your data warehouse or your relational databases and more into your data lake and run product recommendation algorithms against a larger data set using machine learning. So this data in S3 can be the primary source for understanding your customers' past behavior, predicting their future behavior, and generating downstream business value. So your data scientists can then develop, train, and deploy machine learning models by connecting tools like SageMaker to the lakehouse storage layer that you have built up and access training feature sets. We talked a little bit about SageMaker, but really it's a fully managed service that provides you the components to build, train, and deploy ML models. And it also comes with an IDE or interactive development environment called SageMaker Studio. This is really the heart of it, where you can upload data, create new notebooks, train and tune new models, and go moving back and forth between steps on your, on your work to adjust experiments, compare results, deploy your models to production, all in one place, doing it in a visual interface. So that's the power of SageMaker. So alongside those AWS pre-trained AI services that provide ready-made intelligence for application workflows, so you don't have to reinvent the wheel, we give you those services, basically give you the ability to not have to have machine learning experience to leverage machine learning. So we talked a lot about multiple strategies, but to summarize, I think we talked about this at the top with Gandhi's call or Gandhi's session yesterday, but a modern strategy, right, is one where you're looking at cataloging your data and storing your data at any scale, and then having the best price performance for your applications and your analytics needs by choosing the right service for the right job. And doing it while giving everybody data access and to the right people, right? Whether it lives in the data lake or whether it lives in a purpose-built store. So you don't have to go around, managing all these sorts of different governance policies across your different services and stores. So that unified governance that automatically allows you to discover, tag, catalog, and keep your data in sync is really powerful. And then leveraging AI and ML to solve business challenges on top of that, whether you want to enhance your customer experience, improve productivity, optimize your business processes, all of those things, accessing the most complete set of machine learning and AI services while being able to also do your downstream conventional operations is really powerful as well. And being able to do that in an integrated environment is really the most powerful piece. So that's summarized here, right? So being able to build sophisticated big data applications, being able to understand your users. We talked about how to segment your users and your data, understanding your data, understanding your use cases based on your users, and then using the right tool for the right job, and leveraging managed services where possible to scale. That is the full picture of consuming your modern data architecture. So with that, I think that is it for my session. I appreciate the time, and I will pass it on to the next person that's presenting. Thank you so much.
That would be me. But we are also going right into the lab. So I'm going to share kind of the link to the next little portion. We've been answering lots of questions in the GoToMeeting question panel. Just to kind of call out to the room, because I saw it come up a few times through the lab. Because we didn't go through the RDS section specifically, and we didn't do the DMS migration from like a relational DB. There's an option in there called Skip DMS Lab, and if you go through there, there's a little portion where you can use the Cloud Shell to just sync in a bunch of CSV data into your S3 bucket, so you can kind of just fill the data lake in that step, and then all the rest of the activities from there, you'll have that data already in the bucket, and all your glue crawlers and jobs will just work. But do note there is a part where there's an optional step, and one of those optional steps requires that previous RDS migration component that we didn't do. So just kind of skip that little optional bit and move on to the next one, and you'll be set. So we had slated about 45 minutes for this activity as well. So it's 11:15 now. So we'll all work on the lab together, and we'll be answering your questions in GoToMeeting as we progress through this one. And then I'll hop back on the horn here in a little bit to close us out after this lab. Oh, and then let me share the link one more time. Send. Cool. So I just got to the part in the lab on my AWS setup where I'm visualizing in Athena. So I'm making, or I'm sorry, with QuickSight using Athena, like the tables that we had created through Glue. So I'm creating some cool visualizations. I'm gonna see if I can make some dashboards and see if they're good and if they're share worthy by the end of this. So we'll all kind of work async, and then we'll chime in here in about 30 to 40 minutes. All right, how's everybody doing with their lab? Any questions? We haven't heard a whole lot, so we're guessing things are going well. I was doing the lab on my end. I think I'll show you my dashboard. It's not the best looking thing. I went a little off script. Went through the lab, did a lot of the glue, set up the glue jobs, did all the crawling, set up the additional jobs in glue data brew to parse the data, run it through as Parquet format, pulled out all that data into new buckets, registered for QuickSight, and started pulling in the data into the analyses. So it's pretty fun to play with, even with just sample data. It's cool to pull in the visualizations to see what you can work with. I'm not sure if you noticed, but there is some pretty useful ways to set up the visualizations. If you're used to things like Kibana or Grafana, you kind of have to know what you want ahead of time. One thing I like about QuickSight is that it's got the ability to just kind of figure out, it's got this autograph for the visual type. You can kind of just pick, you can click on your data set and see what it'll automatically generate for you. I'm just picking random stuff. It's not going to look pretty, but you know, given the inputs, you know, this little autograph thing is pretty useful. One thing I noticed on mine, at least, there is a data type for location info, and there are a couple visual types to be able to plot information on a map. So pretty cool if your data set has any like geospatial information like latitude and longitude, or even like state, county, or zip codes. You can visualize that data on the map. It's pretty useful. But here's my little dashboard. I'm sure everybody else's will look much nicer than mine. But I made a few analysis from the data set and made this dashboard. It's not my system, it's not my data, so I'm kind of just messing around playing with the data set. But in a situation where I'm running my own platform, or I'm part of a data engineering team or a data analytics team, having the ability to crawl through data sets and quickly change visualizations and modify data on the fly to build these real-time reporting dashboards is very useful. So everybody will still have quite a bit of time remaining for their labs. So I would urge you all to go through and complete whatever components of the lab you were interested in doing, and just see if you can get through the whole thing. It's all good info. Oh, one other cool thing I wanted to call out specifically. When you're in the analysis, one thing I thought was cool, in this Insights tab, you know, QuickSight, you can have QuickSight just kind of generate some just automatic insights from the data set that it's finding, right? So it'll pull in, it likes to do like the top 3 and the bottom 3. It'll pull in some just easy to plug in things, right? And it gives you this little plus sign. You can just insert it as a visualization. That'll all kind of help feed the dashboards, but useful feature there. Okay, and with that in mind, I'm going to close this out. So I'm going to bring up our kind of little 60-minute assessment offer slide here. Melissa, if you're there, I'd like for you to kick off that poll now. But we basically just want to poll the room and get a sense for anybody who's interested in speaking with Mission to talk more about some data project or some initiative. And you know, we're happy to help and talk through anything, even just high level consulting. You know, any way that we can help, we'd like to. So we'll let this poll fly for a couple minutes here and collect some answers as we prepare to close up the event. Cool. Poll is closed. Thank you all for your responses. Thank you all for attending. Final shout out. This offer does include like a 25% off. So if you're, if there's definitely work to do on the roadmap that you're looking for a partner to help with, we were offering a discount if you're coming to us after taking this assessment. Okay, and with that, I believe that's a wrap. Anybody else have any kind of closing statements? Okay, I'll take that as a no. Thank you so much for attending, everyone. We really appreciate your time.